Hello class, Professor Anderson here. Let's talk about the electric field of a dipole, and let's see if we can derive exactly what that electric field looks like. So let's draw a coordinate system here. Here's our good old XY coordinate system. And now let's put a dipole on there. So we're going to make the positive charge right here. We'll make that blue. And we'll make the negative charge down here. We'll make that orange. Okay, so this one is negative, and the upper one is positive. Okay, this is what a dipole looks like. Two charges, positive and negative. Now, why do you even care about the electric field of a dipole? Well, one reason you should care is just about everything in the universe is made up of dipoles. You've got atoms that have positive charges and negative charges. You've got molecules that have positive charges and negative charges. In fact, stuff like water, most of the positive charge is gathered around one end and the negative charge is gathered around the other end. It has a built-in polar moment to it. And that's why water kind of sticks together real easily. Okay, so let's see if we can understand the electric field here. And let's think about the electric field up here at this point right here at a height y above the origin. And let's give this one more parameter here. We're going to say that this distance between the charges is s. Okay? So what does the electric field look like up here at the position y? Well, we know that a positive charge has electric field lines that are going out from it. So there's going to be an electric field here due to the positive charge that is pointing up. But we also know that, ooh, my electric field line is dripping a little bit. You see that? That's kind of cool. Okay, but we also know that the electric field from the orange, from the negative, is going to be pointing down. And in fact, that one going down is not quite as big as the one going up. Why? Because the positive charge is a little closer to where we are than the negative charge. All right, so with those two, let's see if we can figure out what the electric field is at that position y. Well, if we call this one E positive and this one E negative, then we can write down the magnitude of the resultant E field. E at the position y is just going to be E plus minus E minus, right? We have positive going up, negative going down, and so we need to subtract those two, and this will give us the magnitude of the electric field. All right, how do we calculate each of those? Well, we know that the electric field of a point charge is this, 1 over 4 pi epsilon naught q divided by r squared. This is the magnitude of it. R is the distance from the point charge to the point of interest. So in this case, for E plus, what do we get? We get 1 over 4 pi epsilon naught. We have a Q. We're going to say that this one is positive Q, and the other one is negative Q. We'll say they have the exact same value, just to make it really, really simple. Okay. And now positive Q and negative Q give us these two fields. The positive Q one is how far away from our point of interest? Well, it's this far away, right? Y minus s over 2. Okay, and remember we have to square that whole thing, right? That's this distance right here. It's y minus s over 2. All right, what about the negative? The negative is also 1 over 4 pi epsilon naught. We have a q sitting right there. And now in the denominator, we are a little bit further away. Y plus s over 2, quantity squared. Okay. Those are the two electric fields, and now we can add them together to calculate the net. So let's do that. E at position y is going to be E positive and I'm going to cheat a little bit because it looks like we have common terms in both of these, 1 over 4 pi epsilon naught and a q in both of those. Okay? E positive, what's left? It's 1 over y minus s over 2, quantity squared. And then we have to subtract E minus, so it's minus 1 over y plus s over 2 squared. All right, that looks a little ugly, but we're going to simplify it, and then we're going to make some approximations to really iron it out. So if I want to combine these things, how do I combine it? Well, it's not too bad, right? I'm just going to make this a Q right here. We move this one up here, we move this one up there, and then we multiply the denominators. So this is just finding a common denominator. So we've got y plus s over 2, quantity squared. That's this guy up to there. Then we're going to subtract this one up there, y minus s over 2, quantity squared. And then we're dividing by y minus s over 2 squared times y plus s over 2 squared. Okay, and now we want to see if we can simplify this out a little bit. So let's make a little room and we will keep working on this. Okay, so let's multiply this stuff out and see where we get. I'm going to square this y plus s over 2, and I get y squared plus twice the combination of first and second, right? So y times s over 2 gets me a half, but I'm going to have 2 of those, so I just end up with a y times s. And then I'm going to add s squared over 4. That's this thing squared. What about the second one? Well, we're going to subtract a y squared, a minus sy, and a positive s squared over 4. Okay, that looks pretty good. And then in the denominator, we still have this, y minus s over 2 squared, y plus s over 2 squared. And now let's look at the numerator very carefully. We have a y squared here, but we are subtracting a y squared right there. So this, in fact, goes away. We have an s squared over 4, but we are subtracting an s squared over 4. So this goes away. What's left is a y times s minus minus means positive sy. So ys plus sy. So we end up with 2 of those. So this whole thing becomes q over 4 pi epsilon naught. And then we have 2 ys. And then we're going to divide by this thing, y minus s over 2 squared, y plus s over 2 squared. And now we're going to make an approximation. A dipole is actually pretty small. Okay, if it's an atom or a molecule, that's pretty small. And if you are looking some distance away from that atom or molecule, your distance y is going to be much bigger than the size of the dipolar molecule, okay, the atom or molecule s. And so the approximation that we're going to make is just that. Y is much bigger than s. And if we make that approximation, what does that mean? That means that this thing is much bigger than s over 2. So let's ignore that. This thing is much bigger than that s over 2. Let's ignore that. And now look what this becomes. And we'll write approximate because we've done this approximation. Q over 4 pi epsilon naught. And now we have 2ys divided by, we have a y squared from this one, we have a y squared from that one, that's y to the 4th. And so one of the y's up on top cancels with one of those on the bottom, and we're going to end up with the E field at y is equal to 2qs divided by 4 pi epsilon naught y cubed. It's kind of interesting, right? The dipole field does not fall off like 1 over r squared. It falls off like 1 over r cubed. As you get further and further away from this thing, it gets much weaker than just a point charge. And that makes sense, right? Because if I have a positive charge and a negative charge sitting right next to each other, they almost cancel out. And so the field out here has got to be pretty weak, and indeed it is. Another way to write this is the following. 2 times p divided by 4 pi epsilon naught y cubed. And we've introduced something here called p, which is the dipole moment. Okay? P is equal to q times s. If you have two charges, plus q and minus q, and they are separated by s, what is the dipole moment? It's that right there, P equals QS. Okay, so this was the first half of the discussion. What's the electric field of a dipole on the y-axis? The next part is going to be, what's the electric field of a dipole on the x-axis? Cheers. Hello class, Professor Anderson here. Let's talk about the electric field of a dipole. And now we're going to look at what the electric field is on the x-axis as opposed to the y-axis. So like we did before, we had a blue positive charge right there, and we had an orange negative charge right there. Okay, so this was negative Q, and this one up here was positive Q. Okay. Let's say we want to calculate the electric field right here at this position X. How are we going to calculate that? Well, let's think about it for a second. I know that my positive charge is making an electric field out there that points away from the positive charge. So I'm going to move my X over just a little bit to give us a little more room. And now let's think about what the field looks like. Okay, the field from the positive charge is going to look like that. That is our E plus. The field from the negative charge is going to be exactly equal in magnitude, but of course it's going to point the other way. This is our E minus. If those two things are exactly equal in magnitude, and I didn't really draw it very equal, but pretend they're equal in magnitude, the horizontal components of those fields is going to cancel, right? One's pointing to the right, one's pointing to the left. But the vertical components of the field are not going to cancel, they're going to add up. So this is the net electric field right there. Okay? That's what we want to calculate right here. What is this E at position X? All right, so we got to figure that one out. So let's give some parameters here. The distance between the charges, we'll say that is S. Okay? This distance to the charge, to the point of interest from the origin, we're going to call X. And so this distance right here, we're going to have to figure out. Likewise, this distance right here. All right, that's not too bad. Let's call that thing R. And now we can calculate what E of x is. We know it's going to be E plus contribution plus E minus contribution, but the horizontal components cancel, the vertical components add, and so we have to figure out this right here. What is this angle theta? Okay. Why that angle theta? Because we really want this component of E plus, and we're going to want this component of E minus. That's the important one. All right. The magnitude of this thing is E plus. So let's draw it just a little bit bigger to make it clear. Here's my E plus. And now there are two sides here. This we said was angle theta. This is, of course, a right angle. What we're interested in is this side right here. Well, if that's E plus, what is this? This is E plus sine of theta. All right, let's just keep it like that for now, and then we'll see how to add these up. So we've got an E plus sine of theta. We have an E minus sine of theta. Okay, they're both pointing in the same direction, which we know is negative. Okay, so we really want a negative sign when we're all done, but we're just worried about the magnitude right now. So don't worry about the negative sign just yet. All right, E plus sine theta. E plus is just the electric field of a point charge. That point charge plus Q. So E plus just becomes 1 over 4 pi epsilon naught. And then we have positive Q divided by r squared. And we're multiplying that by sine theta. What about E minus? E minus is also in magnitude, remember, we've already taken into account the signs. 1 over 4 pi epsilon naught, Q over r squared, sine theta. Hey, in magnitude, it's the exact same thing. That is super cool. We can just combine them and not worry about it. So we got 2Q sine theta divided by 4 pi epsilon naught r squared. And now we have to think a little bit about this r. What is r? Well, that's r. It's this hypotenuse of this triangle right here. So r squared, we can probably write that out. Because the hypotenuse squared is just equal to one side squared plus the other side squared. And so it is x squared plus s over 2 squared. What about this sine theta? Sine theta is a tricky one. Let's figure that out. Let's draw this a little bit bigger. Okay, so we have r going all the way down. We have an angle there, theta. This is x. This is s over 2. But if that is angle theta right there, this is also angle theta right there. And if I think about this angle theta, knowing that's the right angle, then I get sine theta equals s over 2 divided by r. And we know what r is. R is x squared plus s over 2 squared square rooted. So let's take this and put it all back into here. What do we get? We get 2q over 4 pi epsilon naught. And then we have sine theta, which is s over 2 divided by x squared plus s over 2 squared. That thing is square rooted, which is the same as to the 1/2. But then we have this one as well. And if I stick that into here, it just raises this to a 3/2. Okay? And so this is what it looks like. Now, we're going to make a similar approximation like we did last time. The approximation is that we're looking at this thing very far away. X is going to be much bigger than S. And if X is much bigger than S, that goes away. Okay, so let's write down what our resultant field becomes. What do we get? We get E at this position X is equal to 2Q times S over 2. The 2's go away, and this just becomes Q times S divided by 4 pi epsilon naught. X squared raised to the 3/2 becomes X cubed. Can everybody see that okay? X cubed. Okay. And now QS, remember, is our good old dipole moment, and so we can write this out explicitly. It just becomes P divided by 4 pi epsilon naught X cubed. And it has a particular direction. What direction does it have? Down. So if I put a minus sign here, I want a y hat right there. It's pointing in the negative y hat direction. Interesting that it also goes like 1 over r cubed or 1 over x cubed. Remember when we looked at the dipole field up here, it also fell like 1 over r cubed. So as you go further and further away from this thing, it gets much weaker compared to the field of a point charge. And again, that should make sense. As you get further and further away, these things shrink down until they're basically on top of each other. And that means the electric field should go away very quickly. All right, hopefully that's clear. If not, definitely come see me in office hours. Cheers. Hello class, Professor Matt Anderson here. Let's talk about the electric field of a dipole, and let's see if we can figure out what it is in general. Before we looked at what it is on the y-axis or the x-axis, but let's say we want to look at it in general. So here's my coordinate system, x and y, and let's draw our dipole. And just like before, we had positive charge was blue and negative charge was orange. And what we saw before was the electric field up here was pointing up. The electric field out here was pointing down. Let's ask the question, what about the electric field down here at the negative y-axis? Well, this one was pointing up. Why? Because the positive charge is a little bit closer than the negative charge. So down here, it might make sense for that electric field to also be pointing up. Why? Because it's a little closer to the negative charge than it is to the positive charge. And that is, in fact, correct. It's pointing up down there. What about over here on the left side? On the left side, by symmetry, we could argue that it must be pointing down. Right? If I flip this whole picture around, it's got to look exactly the same. So this is what the electric field looks like on the axes. But what about at an arbitrary position? If we were looking out here somewhere, what would the electric field look like? Well, we could probably reason that if it's positive there and it's negative there, it's got to be something in between those two out here. All right? And let's say some arbitrary position would look like that. As you come down, you're going to rotate towards the negative, then you're going to rotate back towards the positive. All right, seems possible. Let's figure it out. What we said was the E field on the y-axis was 2 p over 4 pi epsilon naught times y cubed. Okay, positive going up right there. The electric field on that x-axis was 1p over 4 pi epsilon naught x cubed. But let's not call them y or x anymore. Let's just call them r. So if I think about an arbitrary point out here, and I call that r, and I also happen to call this angle right there theta, how can we put this together? Well, first off, let's do this. This is 2p over 4 pi epsilon naught r cubed. This was p over 4 pi epsilon naught r cubed. But they do have directions, so let's be a little bit careful about the directions now. What is E? E is going to be some x component and some y component. The x component we said was this, p over 4 pi epsilon naught r cubed, and it's pointing down, so that is in the negative direction. EY is pointing up. And so we keep that positive. Now, we're not quite done here because we haven't put any vector signs on anything. And this is where we need to be a little bit tricky. If I think about r as a distance away from the origin, I'm going to move this out of here for just a second. Then r increasing outwards means that the unit vector r hat points in that direction, away from the origin. What about theta? If theta is measured relative to the y-axis, then theta increases as you go down in this direction. And so look, this is now my new coordinate system, r hat and theta hat. I need to add one more thing here, which is the following. I need to put in some theta dependence on these. If I'm all on the y-axis, or I'm all on the x-axis, what are my particular thetas? Well, if I'm all on the x-axis, then theta would be 90 degrees. If I'm up here on the y-axis, then theta equals 0 degrees. So whatever I put into this equation, I need to make sure that it satisfies the correct limits as theta goes to 0 or 90. When we are at 90 degrees, our electric field is pointing down. And so this term right here, we need to put a cosine theta on. Why? Because cosine of 90 degrees is a value 1. And so that means that we keep this term. It's pointing negative. What direction is it pointing negative? It's actually pointing in the negative theta hat direction. As that line comes down to the x-axis, theta hat is now pointing down. What about this guy? Well, if we use cosine in this one, it makes sense that we would use sine on this one. And let's see if that works, okay? I'm not convinced that it does, so we'll try it. Sine of theta, and that's going to be an r hat. Let's see if that works. As I go to 0 degrees, sine of 0 degrees is 0. That doesn't look very good. Did we do something wrong? I think we did something wrong, right? Because cosine of 90 degrees is in fact 0. I think we said it was 1. So that means we have to flip these two. And this is a good exercise, right? You try it, you make a mistake, but you keep going, and when you double check yourself, I realize I made a mistake. This is in fact the one that should be sine. This one should be cosine. And now let's see if it works out in our limits. If theta equals 0, I'm only going to keep this one. And what's the direction? It's r hat, away from the origin. Good. As I go to 90 degrees, now I'm down here on the x-axis. I'm going to keep sine of 90 degrees, because sine of 90 degrees is 1. And that means I'm in the negative theta hat direction, which is pointing down. Okay, so this does in fact work out. What's the E field of a dipole? And let's be explicit, we're talking about as a function of r and theta, it is just this. We've got a negative p sine theta over, actually let's factor out some common things, because we do have some common factors. What do we have common? We have a p over 4 pi epsilon naught r cubed. Yep, that's in both of them. And then the first, I'm going to switch the order just for fun. I'm going to put this one first. 2 cosine theta r hat minus sine theta theta hat. Okay. This is the general equation for the electric field of a dipole. Given that your P is pointing up, negative and positive, as arranged right there. All right, you can double check this for these other limits and make sure that it works out. Hopefully it does. All right, cheers.